Canvas, and it's like a short crash course or introduction on Firedrake. And then you guys can choose me and ask questions, and I'll help you guys debug. So the example will be just a 2D Poisson equation that we have been solved before in the problem sessions. And you can set your Dirichlet and Neumann boundary condition. And for today, I will not cover specifically on a Neumann boundary condition. I can give you guys some hint on how to do it in Firedrake, but that part is one of the major part in the homework. The second part of the homework, and today I will be playing around with different Dirichlet boundary condition, so you can get familiar with Firedrake. And I guess you guys are very familiar with the 2D Poisson equation. So here I just set two constant where one is f, the other is k, kind of like the example in the lecture notes. And we have a rectangular domain. In your homework, you have a slightly more complicated example or problem. You have some square holes and you have some corner in the holes. And based on that, you can discuss the convergence rate, because the sharp corner will slightly affect your result. And you can also think about what if you have a circular hole in the homework. But for now, for this problem, for the tutorial, we just have a rectangular domain. We don't have any weird geometry. And you have your x +1, -1, and your y +1, -1. And the key step is you first need a mesh. So we provide the mesh in the homework. And one of the questions you can think of is, in the tutorial, I directly use Firedrake mesh generation. But when I provide the mesh function in the homework, how would you define your Neumann boundary condition according to the mesh? And is the Neumann boundary condition implemented exactly? And the variational formulation for the Poisson equation is just this. And I'll just run the code for this example. So basically, you guys already familiar with this. You just install Firedrake, and you need to connect to your Google Drive. These are the steps you have to go through. It's problem section right now.
Oh, okay. So did you not forgot?
Yeah.
Okay.
Oh, did you lock the door? Oh, were you inside?
It might take a while to install the software. Okay. So finished. Oops. Okay. It's take a while. Okay, and I'll be using Gmesh just as was covered in lecture to generate the mesh. If I rerun it, it's gonna show me that they have the software installed. And now I can start generating a mesh. So you can set the how many mesh element do you want in your domain. So I was using rectangular domain and 25 by 25 to generate a square mesh. And you can visualize your mesh. And I didn't set physical group, and this is actually connected to how to implement normal boundary condition. You can try to make some connection with your homework, or sorry, computing project. And maybe one of the questions you can think of is if I just use the default meshing from Firedrake, can I implement normal boundary condition? And so I initialize my space just like what you did in your homework. You can set the order of your space, and so you have your test and trial space, and you can set your constant accordingly. And we already know what's the bilinear form according to the document, the PDF I just shared. So you can just code your bilinear form and also your linear form without a normal boundary condition. And you can run this code. Okay, and so now we begin with the easiest Dirichlet boundary condition where it's all zero on the boundaries. And you just run this boundary condition, and the solution is in the previous base, the base space you just set, the order of your space with the function, and then you solve linear form by linear form equals to linear form. You want to get your solution, and you set your boundary condition. And it's one thing we have to notice is when you set your boundary condition, you're just imposing your Dirichlet boundary condition here using Firedrake. And so this year, we're probably not going to use Phoenix because we try to explore how do we set up the problem of using Q1 and Q2 element in Phoenix, and unfortunately, it was not very successful. But basically, if you know how to use Firedrake, Phoenix will be pretty easy for you. And so basically, when this cell is finished, you already have your solution, and you can visualize your solution from your U solution, and you can show it in 2D and also visualize it 3D. And this is what we kind of expect from you guys in the homework. And that's pretty much it. It's actually quite simple. So you don't have to do all the complicated coding for your bilinear and linear functional. I mean, you still have to do it for CP2, but for the Firedrake part, it's actually quite simple because you imagine you have a bunch of function and you set your basis function and all the local to global map, you write your LG matrix and do the global assembly and impose your Dirichlet boundary condition. In Firedrake or in Phoenix, it's kind of same. All you need to do is just define your boundary condition as a Dirichlet boundary condition, and you put your boundary condition into this solve function, and you run this, and all the complicated global assembly, you write your function for A and L, all that stuff is just as simple as it is. And so for this tutorial, I'm just gonna explore a few more options in the Dirichlet boundary condition. And you can ask me about the knowing boundary condition. I can give you some hint, but I won't just provide you as it is because it's actually one of the key parts in the computing project. So if we don't set the Dirichlet boundary condition all on 0, we can set a specific Dirichlet boundary condition on boundary 2. And if you set it and you run the same code, your solution is in the functional space V, and you solve your solution. You solve the problem and obtain your solution use solve, and you can visualize it, and you'll see how this Dirichlet boundary condition change your solution. And another, let me try to annotate. So another possible boundary condition we have is if it's on a boundary, you have something like this. Recall your homework 5 or homework 4. you can set your boundary condition as u equals x or something like that. You can also do that in Firedrake or Phoenix. All you need to do is recall your mesh and get your spatial coordinate system, and you have your x and y, and you set your boundary condition as x or y, and you can impose different functions like sine or cosine, apply wave function, etc., etc. So basically you run this, set your Dirichlet boundary condition, and solve your problem, and you'll be having different solutions, and you can visualize. So this is what we kind of expect in for your homework. Just try to visualize in 2D and 3D and submit your result. Let me see, there's a chat. Okay, so what are the input arguments you're putting in the function? So for the Dirichlet boundary condition, there's a function directly can cause, because I didn't define this function Dirichlet BC. This is from Firedrake. So in Python, when you do this from Firedrake, import all the function in the library, it contains all the stuff you need. So this Dirichlet boundary condition or Dirichlet BC, this function contains what you need, and you set your space and what boundary condition you want. Let's start from the simplest. Like you set your the solution space and the boundary condition, and you want it to be on all the boundaries, on all the 4 boundaries, 1, 2, 3, 4, or on specific boundary. So this is the argument you put into your Dirichlet boundary condition. And you solve this, and you can visualize the result. Okay. Yeah, that's actually quite short. It's 10 minutes. That's basically the tutorial for Firedrake. So the point is, we hope you can see from your CP1, just for a 1D problem, you have to write all the function for your bilinear and linear functional, and it's very complicated, but you really fundamentally understand what is going on in finite element method, and you have to encode both your normal and Dirichlet boundary condition and learn how to do the global assembly and obtain a solution. So for this computing project 2, in the first part, you're doing the same thing as your CP1. You're basically adopting this almost the same code from CP1, just but it's actually quite complicated to extend it to 2D. And after that, we wanted to see how easy it is to use open source project like Firedrake or Phoenix, that you're solving the same problem as you did in CP1, but all you need to do is just import all the function that's already in the open source library, and you can set your Dirichlet boundary condition. And so you'll be able to use open source software very fluently, and you understand, wow, using this kind of software, I'm not using commercial software, I'm still seeing the source code, and I know what's going on in my code. I understand the math and basics when I'm doing any calculation, and you should be able to obtain the same result and be familiar with how to imposing different kind of boundary conditions. And that's basically it. Yeah, maybe I'll stop recording because it's quite short, or anyone has any questions, like very general questions, I can still put in the recording. And then I'll stop recording, and you guys can share screen, and I'll help you debug your code if you don't want that to be part of the recording. Okay, this is a location part going. Yes, that's actually a very good question. So Marshall was asking about the knowing boundary condition. I deliberately not mentioning that in the tutorial because that's actually a key part, or like a difficult part of your computing project. So I'm not giving it as it is. So the way to implement Dirichlet boundary condition is very straightforward. Just recall the function and put whatever value you want to put and impose it as Dirichlet boundary condition. So for knowing boundary condition, you have to think about how to implement it. I can give you some hint, maybe put this part in the recording. So it's related to the mesh, right? If you can simultaneously pull up your computing project too, the code we give you guys. Here, I'm just generating a mesh using the default meshing function rectangle mesh from Firedrake. But in a homework, I didn't write the code. So there's a long function, CP2 mesh or something like that. You also use gmesh to generate the whole mesh. But if you read that function, there's add physical group. And given the add physical group, from the mesh, you will have something like DS or something that enclose or represent all the boundaries. And because you already have different physical groups, so you already define what's the physical group 1 and physical group 2, etc., and or any number. And you have to think about how to impose your Neumann boundary condition according to the specific physical group of the domain. Because here I didn't define a physical group. You can imagine if you define a physical group accordingly, where you can have a hole in your domain, then you can recall exactly what boundary are you referring to and put that into your linear functional or the force vector as part of the force vector, and you can impose your Neumann boundary condition. I don't know if that answers your question. But yeah, so to impose your Neumann boundary condition, one way to do it in a computing project too is to recall the physical group and put that into your force vector or linear functional or L. And then you do the same thing. You still try to solve A equals L. And remember, the BCS equals BC here, at least in this code, or in general, this is the place you're imposing the Dirichlet boundary condition. And the place you want to impose the Neumann boundary condition is somewhere here, right? Any more questions? Maybe I'll stop recording at 5:50, and then we'll have like more flexible office hour, and you can share screen or come to 5:20, and I'll help you debug your code. Thank you. Yes. I'll post a recording on Canvas. Maybe I'll keep recording for 2 more minutes. And I'll